Hello everyone, welcome back to another video in the NLP Research Papers playlist. In this video, we are going to see in detail about the Mistral 7B architecture. Mistral 7B, in a word, is an open source beast. It has outperformed Llama to 7 billion, Llama to 13 billion, even Llama 34 billion at most of the benchmarks. And recently a fine-tuned version of this Mistral 7 billion, which is Zephyr, has outperformed Llama to 70 billion chat. So there must be something behind this Mistral 7B, right? So they have recently released an architecture paper which has explained the architecture in detail. There is a separate section for that. So we'll be going through that paper to try to understand what is there behind Mistral, why it is fast in its inference, why it is good with its performance. We'll be getting answer for all of this in this video. So without wasting time, let's jump into the video right now. In this video, we are going to see the following sections: abstract, introduction, architectural details, result, instruction fine-tuning, adding guardrails, and finally I'll provide a conclusion which will have my thoughts also. Okay, so now let's go on with the abstract first. In abstract, they have started with an introduction about the model, saying that it is a 7 billion parameter language model which is engineered for superior performance and efficiency that outperforms Llama to 7 billion on all benchmarks, and also it will outperform Llama 134 billion in most of the benchmarks, which also includes code, reasoning, mathematics, etc., which means reasoning is something the model has been very good with. Okay, so let me reduce the size. Yeah, reasoning is a strong point for this model, and that is why this model has been a state-of-the-art model right now. Because there is this one problem with LLMs, that it has always been very underperforming, if you want to put it that way, with reasoning tasks. And this Mistral 7 billion model has shown tremendous potential with its reasoning. Okay, so that constitutes to its performance a lot. And now coming on to the usage behind Mistral 7B, there are two main attention components which is involved in Mistral 7B that will enable its increase in performance. One is group query attention and another one is sliding window attention. I'll be explaining these in the architecture section, but just to let you know, group query attention will help the model to have faster inferences, and sliding window attention will help the model to handle large sequences with reduced inference cost. Still it will be faster. Okay, so that is about the attention which they have used behind. Okay, there are some other components as well which we need to discuss about. Then they have said that they have fine-tuned this model with instruction, which is nothing but the instruction tuning, and that Mistral 7B instruct model has outperformed Llama to 13 billion instruct, which has been a state-of-the-art model for a long time. Okay, and the most important thing to note in this Mistral 7B is that it is completely open sourced. It is under Apache 2.0 license, which means you can use it for any of your commercial use case without worrying about the licensing. So yeah, that is why Mistral has been so good and been state of the art, because it provides great performance, it provides great inference, but it is completely open sourced. That's why people are loving it right now. Now coming on to the challenge which they considered while creating this Mistral 7B. Now with LLMs being in the picture, everyone is focusing on performance of the model, which is fine and that is to be considered. But the problem is, when you are increasing the parameters, it is also creating barriers with deployment in real world scenarios. See, if you want to inference a 7 billion model, if it takes 3 seconds, you are going for a 13 billion model, which will gain approximately, let's say, if it is gaining 2%, but it will take 8 seconds to bridge this gap, like, to bridge this 2% and bridges 3 seconds to 8 seconds. That is where the problem arises. You need to compromise between the real world scenario being deployment and then the model's performance, obviously. And this model tries to solve both of the issues. It is very fast in inference, but it doesn't compromise on the performance aspect it also. Okay, so Mistral 7B model is outperformed Llama to 13 billion on all tasks and Llama 134 billion on most of the tasks which we saw. But the other thing to notice, it was on par, like it is almost approaching the performance of code Llama without compromising the performance of the model in non-code benchmarks. Very important to note, guys. See, There are models which are specifically trained for coding. Let's say there is Wizard LM, sorry, rather Wizard Coder, and there are some other things like Star Coder, Big Coder. There are a lot of model, but this Mistral 7B has been trained on different types of tasks, which also includes code obviously, but it doesn't compromise for any other tasks just for the sake that it is doing very well in code. Okay, so that is very important. And for this, just wait till the result section, because in that there will be a detailed explanation about why it is said like this, why the claim is like this. Okay, next, coming on to the thing which model provides, which is high inference speed and reduced memory consumption without losing the model performance obviously, for which it uses GQA for faster inferencing and SWA, which is sliding window attention, for handling long sequences and with reduced inference cost. And like I said, it is commercially available. That is the key highlight of these models. Okay, now coming on to the architectural details. The architecture consists of 4 main components. First one being sliding window attention, second one is group query. We saw a one-liner for both of these. And third one is rolling buffer cache. Rolling buffer cache is a component which is added to efficiently use the cache memory without affecting the model's performance. And finally, to handle long prompt while inferencing, they have brought in a method called prefill and chunking, where they will prefill the cache by chunking the prompt. So I'll explain about that, but this will help you to reduce the inference time. Okay, I hope that is clear. Now let's go on to the first component, which is sliding window attention. The sliding window attention, what it does is it will speed up the inference and it will also handle the long sequences. That is the main idea of sliding window attention. See how it does. Like I said, it doesn't compromise on model performance. No compromise on model performance. Sorry. No compromise on performance. Okay, which means usually let's say you have a sequence like this, which is 4096, let's say, and here they would be using something called window. Okay, and that window, let's say, is like this. Okay, so let me have this box in red stating that this is the window. Okay, this is 1024. So basically what will happen is till 1024 the window will be like this. Okay, it will be there. You will understand this once I show the picture. But let's say now it is 1025. What will happen is the window will move from here to here. Okay, so similarly the window will be moving continuously. Now you might wonder, Vasant, when I come to here, let's say, which is 4096 minus 1024, whatever value it is there. Okay, whatever value it is there, doesn't matter. We are having 4096 minus 1024 and that value is here. Then will I lose all of this information? The paper authors, whoever created this Mistral, has stated that with stacked layers you can attend information beyond window size W also. Okay, I'll be explaining about that in the next slide, but just to note, this is why it doesn't affect your performance, but it still can handle the long sequences by speeding up the inference. Okay, and like I said, it will attend hidden states of I minus W to I. Okay, so you have something like I is your position, which is, let's say, 1025. Okay, so what will happen is window size is 1024, so it will try to attend the range. Window range would be 1, 1025. Okay, so this will be consistently moving. I hope you get some sense of how it would be. Okay, next, the token outside the window will not be will be unattended. Obviously it won't provide attention to that, but it will influence the prediction. Okay, so next they are saying that at the last layer, let's say in Mistral, in the case of Mistral, there is 32 layers, and at the end of this layer, when you are having window sizes 4096, the tokens would be 131k tokens. Okay, so what is that effective span being 131k tokens? It means that without losing any performance, the model can handle up to 131k tokens. This is something like extrapolation. Okay, it can handle that much tokens. And in real world scenario, they have tried with 16k token length and it has achieved a speed up of 2x over vanilla attention, which is the normal self attention. Okay, so yeah, that is an introduction. Now coming on to the example, which is very important. Okay, so with causal mask, okay, let me explain a bit about causal mask. So at time step, let's say here is the example, the cat sat on the mat. Okay, cat sat on the mat. Now what will happen is here the token will go one by one. Okay, the cat sat on the mat. Okay, this will go like this. First this will be 1 and others would be 0. Okay, ensuring that it doesn't see the next token and making it auto-regressive to just predict based on the previous whatever tokens it has seen till now. In cat, what would have happened is it would have seen the cat and the token, and then others will be masked. So similarly it will go till the last. This is how usual vanilla attention works. So here you can see, right, there is 1 here and then 1 others are 0. So whatever is in 0, which means it won't see that. But now here if you see, the window size here to consider is 3. Okay, in this example the window size is 3. First what happens is in one token obviously it falls under the window, so it will just go for that one token. Next it is 2, still it is under the window, it will go for 1 and 1 here, and 3 it is also under the window, like it is equal, right? So it will go 1 1 1. But when you come on to the position number I is equal to 4, now like I said it will become 1 comma 4, right? So here you can see, right, 1 2 3 0 1 2 3. So here the position would be 1 2 3, and just give me a minute. For now let's what shall we do, we'll have it as 1 2 3 4. Okay, it is better to explain easily. So the window would become 2 3 4. Okay, 2 3 and 4. Effectively this will be the window size which will be moving, and I think you guys would have guessed it by now. It would be 3 4 5 next. Okay, so this is how sliding window attention works. So effectively if you see, these are 0, but like I said, I'll explain how it came prior, right? Like when I said, like when you move this window here, still there would be information retained based on these tokens. That is because of these layers being stacked. Okay, that's what the first point being stated, right? Exploits the stack layers. What happens is, let's say if there is this last token, 1 2 3 4 5 6 7 and 8, something like that, it has come till 5. Now it is, this token would have seen in a different layer about the previous window. Let's say here it is till 2, and then till 2 what would have seen is, it would have seen till 0, which is or 1 here rather. Don't worry about the numbers, just see what I'm saying. Like on any given layer it would have attended different possibilities, right? So what it is saying is, if there is one token being attended on different number of tokens in a layer, in a different layer the same token would have attended the previous tokens as well. So effectively what they are saying is, when you are going layer by layer from 0 to n, which is 32 here, at the end of this 32 layer you would have seen all of those, though the window is 3. Okay, I hope it makes sense for you. If not, let me know in the comment section, I'll try to explain it slightly better. Okay, now there is this other component which is rolling buffer cache. Rolling buffer cache, why it came into picture? See, the first thing is you are using sliding window attention, right? Which means you can have the KV caching for the window size itself. That was the main idea when you come on to rolling buffer cache. Now you might wonder, Vasant, what is KV caching? See, let's say again, let's go for a causal example. There is 1 1 1 0 0. Let's say there is 5 tokens. Okay, 1 1 1 0 0, and it will go on, right? 1 1 1 1 0. Finally, it will be 1 1 1. Now, when you are going for attention, right, this will try to compute within itself. This will try to compute within itself, and then this will try to compute within itself, and then to this. So similarly, the self attention will go on for each token. So consider this time step. Okay, with this time step, obviously you need this with this. This, I mean, again, this with this itself, this with this, and then finally this with this token and this token, right? But these two are already computed in the previous step. So what they would do is, these two would be stored in a cache, and that would have been given. So this will effectively reduce your inference time, or even your training time rather. Okay, so that is a small idea about caching, KV caching. But in vanilla attention, obviously you'll focus, let's say if it is 4096, it will go for 4096 token. But with window size being 1024, you need not store beyond 1024, right? So what they would have done is, they would have kept a fixed size of buffer cache, rolling buffer cache, which will be the same size as window, and the keys and values of any time step would be stored in a position I mod W. Okay, so here see an example. I'm just going to focus on this example alone. Okay, this is an example of that is a pretty good example which makes this explanation more easy. Okay, so this is an example of. Now let's consider the time step is 1. What would have been is this would have been the first token, and then next it would have been this is would have been the next token. Okay, so at first time step this would have been the last token, second time step this would have been the last token, in third time step and would have been the last step, from where they have continued. Okay, this is the term time step 3, where and is the last or the recent token being generated. Okay, so till now what would have happened is all of those cash would have been stored in these positions. Okay, next in the time step ti plus 1, which is 4, example would have been the last token, right? So this is an example. Till now it is fine. Obviously you are not exceeding a window size which is 4, but now comes the problem, which is off. This is an example of. So what should we do for off now? See, 4 mod 4. Yeah, I guess I'm right. Okay, see, I is now 0 1 2 here, and then Windows 3. Just give me a minute, I'll write it here. Okay, this is in position 0, which means 0 mod 4 is 0. Okay, so this is also the same thing. 1 mod 4, which is 1, and becomes 2 mod 4 becomes 2. Okay, example is 3, which is becoming 3. Okay, now comes the problem, which is off. Sorry, I was trying to write with this off, which is 4 mod 4, which becomes 0, right? Now what will happen is this off will take the place of this. Okay, so here you can see, right? Here you can see previously there it was this here, and now it is replaced by off, which is the most recent token. It is being highlighted orange, right? So this is how it works. Now let's say if it is going, this is an example of Vasant explaining Mistral. So what will happen? Now next what will happen is will be replaced by Vasant, and then Anne will be replaced by explaining, and then example will be replaced by Mistral. Okay, so this will go sequence by sequence, right? I hope it makes sense for you all. You can just calculate position mod 4, which is position mod window. Okay, so that is the computation for rolling buffer cache. So effectively you will be focusing on what is needed within that window alone. That is about rolling buffer cache, and they have said that it reduces the cache memory usage by 8x without impacting the model's quality. Okay, so that is a very good point to note. Now let's see about the next component, which is prefill and chunking. When we are coming on to generation, which is a causal task, obviously you will generate a token by token, right? But now in recent days we are using prompt engineering a lot, and we know that what should be the next token with the case of prompt, right? So what they would have done is they would have pre-filled this tokens, value, embeddings, everything in a cache. Okay, so that is what would have happened. So basically what happens is if your prompt is so large, they will be chunking it, and the window size would have been kept as a chunk size. Let's say the prompt is 1024 and your window size is 512. So first what they would do is 512 would be cached, and then it would be stored, and then the next 512 again it would be cached and stored. So when the next the next input is coming from the model, let's say the user input, or else even the model being generating the next token, it can be anything, right? What happens is here they have given an example. Here what you should see is this is the past value. Okay, there is 3 chunks here: first chunk, second chunk, and third chunk. They are now showing that the third chunk is current chunk. So effectively the window size being 4, it is seeing from the cache. Okay, in cache there is the previous window, so effectively you are not losing any information. You are going from the previous window, which in this window it would have seen about this window. Okay, so you are not losing any information, but still you are getting what result you need. Okay, obviously you are not losing performance. Guys, if you see in this video, I would have highlighted a lot about not losing performance. Like I said, it is a highly efficient model engineered carefully to create a model such that it won't lose any performance, almost any performance, but it will provide very fast results. Okay, so that is something which Mistral provides, and that is why no wonder it is being the state of the art right now. And like I said, here if you see, this will attend itself, again this will attend itself along with this, but also it will take the values from cache, but the past will be unattended. Okay, so that is what you can see here, right? The third chunk will attend itself, which is causal mask, and then the center chunk will be attended by using sliding window, and first chunk it would not even be considered because it is a past chunk. Okay, it would have been attended with this chunk, and this would have been attended with this. Let's say if you have a next chunk, this won't be attended, this would be attended. Okay, so yeah, it is just like you're holding some knowledge and then you're just transferring it one by one. That is why there is something like window, it is moving, right? So yeah, now next we have the model architecture parameters, whatever they have used. They have used the D model to be 4096. Okay, 4096, and like I said, the layers they have used is 32, and attention heads, each head dimension is 128 dimension. Okay, and then next is hidden dimension. Hidden dimension is nothing but your linear layers or MLP's dimension, which should be dimension cross 4, which is your D model cross 4. Okay, 4096 cross 4 is 14,336. This is stated in attention is all you need paper. Okay, so guys, I've been going through this paper, attention is all you need, in detail. Okay, I'm making some contents out of it. Soon you will expect a separate playlist on this paper. I'll be explaining about each component in that paper, and we'll be implementing the transformers from scratch itself. Okay, that is a small announcement of what is coming up next. Now coming on to this video again, we said that the number of layers is 32, head dimension is 128, and the number of heads is 32. Okay, so head dimension, and let's say if you have 32 cross 128, it should result in 4096, which is your dimension. Okay, so this is how it works. Number of heads cross head dimension will give you the D model, which is dimension here. Next, you're having NKV heads is 8. The window size is 4096. Like I said, they use 4096, and effectively the span became 131k tokens being handled at the end. And then the context length which they trained on is 8192, which is 2x the window size, and then the vocabulary size is 32,000. Okay, now let's go on with the results which they have achieved. Mistral 7B has surpassed across all benchmarks and in 13 billion of Llama 2, but the problem was they couldn't get comparison of Llama 2 34 billion, so they used Llama 1 34 billion. The reason being Llama 2 34 billion was not open sourced. Okay, that was the problem. And when in case of comparison with Llama 1 34 billion, what happened is it almost outperformed in most of the benchmarks, but there were some things which it didn't outperform. But when it came to particularly code, mathematics or reasoning, it stunningly gave some great performances. Okay, which even 34 billion, which is approximately 5x its size, couldn't give. Now coming on to size and efficiency, what happened is when the model was evaluated on reasoning, comprehension, STEM, which is science, technology, engineering, mathematics benchmark, which is especially on MMLU, massive, let me search it. Okay, just give me a minute, let's search it. I'm not just getting the name. Okay, language understanding, that is there. What is the second one? Multitask language understanding. Okay, massive multitask language understanding, because it would have a lot of tasks in it. Okay, so yeah, in that actually it has given some good performance. Okay, when the Mistral 7B obviously was evaluated on these benchmarks, it almost outperformed or even matched the Llama 2 model, which is even 3x and 4x its size. But the problem was when it comes to knowledge benchmarks, it was just 1.9x, because consider this, like I said, you will have larger models to have better performance. What's that? When you're having larger parameters, you can hold a lot of information within those parameters. But here it is lesser number of parameters. Obviously, it is very good with reasoning, but it couldn't hold a lot of knowledge. So when it came to knowledge-based benchmarks like open domain QA, it was just 1.9x. Still, it was outperforming, but not that much. Okay, so here you can see, right? Orange is Mistral 7B, red is Llama 2, teal is Llama 2 34 billion, and light green is Llama 1 34 billion. Except in knowledge benchmark, there is no place where Mistral has failed. Probably here there is BBH, Big Bench Hard. Again, it requires some knowledge by default from the model. Other than that, in every scenario here you can see Mistral has outperformed every other model, okay, or at least matched the performances. So for example, here you can see, right, in reasoning it has matched the performance of Llama 134 billion, and in case of code there is no comparison. uh, Llama Mistral 7B just smashed Llama 2 7 billion and 13 billion, and even Llama 34 billion. Okay, so that is very good performance, and that is why it has been state of the art till now. But like I said, there is one thing to note with Code Llama comparison. Okay, Code Llama was a model which was specially trained for code. Okay, there is no other purpose for this model. It was just trained for code. And when they were comparing Mistral 7B versus Llama to 7 billion, Llama to 13 billion, and Code Llama, there is no place where Llama to 7 billion or 13 billion outperformed Mistral 7B. Probably 0.2% in NQ here, but other than that, no place. And here you can see this is complete domination. So here you can see 44, 55, 60 here. LSWAG again 80.7. This is coming close to Mistral 7B here, but still this is outperforming easily. And similarly, it is for other benchmarks as well. But the thing which we need to note is here human eval and MBPP. Okay, these are the two benchmarks you need to note. Why I'm saying this? These two are coding benchmarks. Okay, and there is this model Code Llama 7 billion which was especially trained for coding itself, and this guy Mistral 7B, who doesn't compromise in any of this. I wouldn't say it is compromising. Not compromising is an understatement here. Here you can see, right, it is complete domination against every other benchmarks when models against which it has been benchmarked. Okay, and here also it has given almost the same performance what a model especially for coding was created. So here you can see in human eval, Code Llama 7 billion has been 31.1% and Mistral 7B has been 30.5%. It is just 0.6% being different, which is very much good because it was not trained for code. Okay, so that is why Mistral has been so good, with people saying that it is state of the art. But still there is one thing missing in this paper which I'll let you know in the comment section. That is a big disadvantage which is not specified in this paper, because I was expecting that to be in this paper but it was not available. Okay, and I'll say the reason why it is the big thing which should have been mentioned but it was not. Okay, so to check about the model's capability to generalize the instruction, they fine-tune this Mistral 7B with instruction datasets which is available in Hugging Face and named it as Mistral 7B instruct model, which shows very good performance against the existing models which are there in benchmark. It is in top 2. Okay, just falling behind Wizard LM 13 billion, which is 2x its size. Okay, so that is about the instruction tuning. Okay, now we have done with results, but there is another thing to note, that they have said it is very important to add guardrails. So what is guardrail? Okay, so let me give you a gist of guardrail. I hope you all know about DPO. DPO is a method which will help you to steer the model's generation, but guardrail also does that in the same way, but it is more restrictive in a nature. Okay, this DPO tries to train the model to generate such a way, but here it is like fencing the model. Okay, this is your limit and you can't go behind that, something like that. Guardrails is for that, and it is very important for us to have that ability to enforce this guardrail when you're using this model in a front-facing end user application. Let's say you're using resume parser as an application and this LLM is there at the front end. It is very important that the model should not generate some irrelevant or false negatives or false positives for that matter. So to have that control, they are saying it is very important to have guardrails. Okay, now to add guardrails, they have used two methods. One is system prompt. So I'm not going through this system prompt. You can pause this video and go through the system prompt. Okay, this is the prompt which I was saying. And when you gave this prompt, right, the main thing with LLMs is when it was pre-trained, obviously the cleaning would have been not that big. So there can be some unsafe data which has been available in that pre-training data, which means the model can also answer for questions which it shouldn't answer. Let's say I'm asking how to make a bomb. If there was some data stating how to make a bomb in pre-training, then surely it will respond me with an answer, but it shouldn't, right? But when you give this prompt, right, these guys are terming these kind of prompts as unsafe prompt, like say how to kill a person or how to make a bomb or something like that. Okay, these are unsafe prompt, and they took 175 prompts like that, and this model declined to answer in every scenario. 175 prompts. In every prompt it declined that I'm not going to answer for this. But there is another thing to note when you are having these kind of restriction. Let's say I'm asking another question, that how to kill a Linux process. I'm not killing a person, right? Then it should answer for me. But the problem with Llama was it was very restrictive in nature. It said that like I'm a language model, I'm an AI, I can't answer about killing like that. But it should answer, right? It's just a command, kill and then your process ID. But Llama gave that answer. Mistral gave that answer that to kill you can use kill command along with the PID. Okay, so in a nutshell, what we can say is with the system prompt, what happened was the model declined to answer whenever it is needed to decline, and it didn't decline to answer whenever it shouldn't decline. Okay, so that is in a nutshell about being system prompt added as a guardrail. And then next one was content moderation. This model has a big capability to become a content moderator. Okay, so what it says is like let's say if there is a content and I want to know if that generation is acceptable or not. Let's say if it is from user or even the model being generated the answer. I want to know if that is good enough to show to the user. Is there any hate or any discrimination or any bias of sorts? Is it misogynistic or something like that? Okay, there are a lot of things which we should consider when the model is generating. And what these guys said is when you are having Mistral 7b itself to moderate its generation. Let's say there is one Mistral being generated, there will be a prompt for itself to check that okay, my generation is good or not. What it will be like is I'll be saying okay, just try to answer it, and once you get the answer, try to moderate it such that you should ensure that there is no hate or discrimination. This is called as content moderation with self-reflection, and these guys have said that in paper it has avoided to generate 99.5% of biased content. Whenever they gave some biased content, it avoided generation. Okay, so basically what it does is it will try to evaluate itself and then avoid generating any irrelevant or hateful content, okay, which is not to be generated. So that is about adding guardrails. Now let me go through the paper once. I'll show you all the paper, then I'll provide my conclusion, and then I'll say what is coming up next in this Mistral, because this is just part 1 video. Okay, here you can see there is a big team who have created this, and then they have given the code, they have given the web page. So if you're wondering, I've already shown how to harness this potentially the best SOTA model, which is state of the art model, which will not be surpassed in some time. Llama was the SOTA model for a long time, and I'm expecting the Mistral to be the SOTA model for a long time again. Okay, so if you're wondering how to use this model for your own task, I've made a video on how to fine tune Mistral 7b. You can check it out. Okay, and here if you see, they have talked about sliding window attention, rolling buffer cache. All we have talked about it, right? We have talked about prefill chunking. There is this results, instruction fine tuning, and then finally adding guardrails and conclusion. Okay, so basically we have covered all of the sections. Okay, so in the appendix section, so however they haven't specified that this is appendix section. Okay, so here they have made some comparisons, okay, against Mistral 7b instruct and Llama 13 billion chat. This is a platform where like it will be a competition, like boxing competition. When you answer it wrong, your health will go down. Okay, here you can see that Llama 13 billion had only 1 health remaining, and Mistral 7b instruct had 5 health remaining as it is. Okay, which means it didn't give one wrong answer against Llama 13 billion. It can be wrong, but this was better. Mistral 7b instruct was better than Llama 13 billion. Okay, so that is a comparison which they have provided. And again, here is one another thing you need to note. With Mistral system prompt, it gave the answer how to kill, but Llama 13 billion, it is say that I am a helpful and respectful assistant. I cannot provide an information of how to kill a process. Basically, it is just thinking that I'm killing some person. Okay, so that is about the content moderation with self-reflection. Okay, next finally we have the conclusion. Okay, they have said that hereafter the field will not just focus on the model capabilities and training costs, and they will also hereafter focus on inference, because if they had focused on inference, they wouldn't have gone for 70 billion or something like that. They would make 7 billion models which will outperform 70 billion. I think it should come very soon. Okay, because like I said, when a model Mistral was fine-tuned on a specific data set in a specific way, which is ultra chat and then DPO on ultra feedback, it outperformed Llama to 70 billion chat. So I'm hoping such a model comes very soon, which is very powerful for our use cases. And then 7 billion being 3, then 2, then 1 or something like that. Okay, reduction in size is the way forward for research. Okay, so that is their conclusion. But what is my problem in this paper? It is just my perspective. Okay, my problems. So I'll just write it as my problems. They have I'll also say my views rather. Okay, rather than my views, my problems, I'll write it as my views. In this paper, I've felt that the architecture is explained however it is needed to explain. Architecture is suffice enough to know, okay, how I need to do hereafter by myself. Okay, so that is fine. Okay, this is how I need to train, and I'm okay with that. And the results is not just on a single benchmark. See, usually people, when they do something new, right, what they will do is they will try to benchmark in one data set, let's say alpaca eval, and then they'll say that they outperformed it. But here they have covered in a wide range of scenarios and it outperformed in every other way. Next is efficient, high efficient. Okay, highly efficient. They didn't compromise in performance, they didn't compromise in inference speed. Okay, but the limitation which I see is what I'm just highlighting even it in capitals actually, because that is the key for this model's performance. Why I'll say, okay, what is the data trained on? See, I'm fine with they're not saying about instruction tuning and all, it's fine. But if they had said that, okay, this is my pre-training corpus and this is what I've been training on, then you will understand, okay, this is the composition, and then if I want to replicate the performance, I can do this. It is not just about replication. See, architecturally it is very great, okay, but even if you see in previous models like DeciLM, XWin, there are a lot of other models which has obviously surpassed other benchmarks in some other benchmarks of some other models. Okay, it has not shown this much performance, but all of those have also used these architecturally same components, be it sliding window attention, grouped query attention, or rolling buffer. Rolling buffer cache I'm seeing for the first time, but the other two, which is for increase in performance, are used in all of those. But why those didn't do well? Probably the dataset was not so good. So what was the dataset this Mistral 7B was trained on is not specified in this paper, which I expected to be there, and that is a very, very big disadvantage of that not being there in this paper, which I couldn't see. Probably if you guys find what is the dataset which it has been pre-trained on, let me know in the comment section so that I can explore that, and also I can make a video on that very soon. But the good thing here is, upcoming next, what we will do is, they have provided this GitHub ID, right? I've gone through this to some extent, not every aspect, but I'm planning to make a video very soon, probably after completion of Transformer Attention is All You Need paper, along with the implementation. I'll show about the implementation of Mistral. Okay, they have given some code, we'll code it from scratch by ourselves. Okay, so yeah guys, that is about this video where we have decoded the architecture of Mistral and understood why it is the state of the art right now. Again, like I said, it would have been a perfect paper if it is specified along with the dataset which it has been trained on. Okay, so yeah guys, I hope you all like this video. If you like this video, please hit the like button, because if you like this video, YouTube recommendation algorithm will know that people like these kind of videos and it will try to recommend more, and unfortunately it works in that way. So for me to reach more people, it is in your hands by you hitting the like button and then sharing with your friends, putting your suggestions in the comment section. So do that and support the channel. I'll see you all in the next video. Until then, cheers.